And finally, scientists believe that we may have caught a whisper from another universe. And this is not a sci-fi film, but a real signal that could have slipped through a cosmic wormhole. The big question is, NASA just confirmed something no one expected. A second wave of signals from the Andromeda galaxy has reached Earth, and it's stronger than the first. The data came through at 3:47 a.m. Eastern Time. Radio telescopes across 3 continents lit up simultaneously. The signal spiked so hard it temporarily overwhelmed receiver arrays at the Chime Observatory in Canada. This wasn't background noise. This wasn't a glitch. The spectrogram showed a distinct pattern, a repeating pulse, the same frequency signature detected 18 months ago, but this time the intensity measured 50 times higher. Andromeda sits 2.5 million light-years away. That means whatever created this signal happened 2.5 million years ago. And now a second burst has arrived. Scientists at NASA's Deep Space Network scrambled to cross-reference the data. Within hours, telescopes in New Mexico and Australia confirmed it. The pattern matched. The timing was impossible to ignore. For the first time since we began scanning the cosmos in 1960, automated AI systems flagged something they couldn't classify, not a pulsar, not a magnetar, not anything in their database. The question burning through every observatory right now, if this is wave 2, what comes next? The first wave arrived 18 months ago, in January 2024. Radio telescopes picked up a brief flash from Andromeda's direction, milliseconds of radio energy. Bright, yes, but not unprecedented. Astronomers catalogued it as FRB 240117, just another fast radio burst, the kind Chime detects dozens of times per year. Most come from distant galaxies billions of light-years away. This one was closer, much closer. But it was a single event, no follow-up, no repeat. The scientific consensus, probably a magnetar, a hypermagnetized neutron star undergoing a violent crustal shift. Strange, but explainable. The data got filed, published in a brief journal note. Life moved on. Then the second wave hit. Mission Control at NASA's Jet Propulsion Laboratory wasn't just curious this time, they called an emergency briefing. Radio astronomers from Chime, the Deep Space Network, and the Very Large Array were patched in within the hour. Every major observatory on Earth was looped into the same conference line. Because this wasn't a repeat in the usual sense. The signal came from the exact same point in Andromeda, same galactic coordinates, but the structure was different, more complex, more organized. NASA's Deep Space Network dishes swiveled to lock onto the source. The massive 70-meter antenna in Goldstone, California, captured every photon. The signal persisted for 3 full seconds, an eternity in radio astronomy. And when the data streamed through, every scientist in that room saw the same thing. It wasn't just noise anymore, it looked patterned. NASA deployed their newest AI analysis system, the same neural network architecture Google DeepMind developed for protein folding, retrained to hunt for patterns in cosmic radio data. The AI flagged something within minutes, repeating polarization changes. Radio waves vibrate in specific orientations, like light passing through polarized sunglasses. Natural sources like pulsars show random or slowly rotating polarization. It's chaotic, messy. This signal flipped its polarization angle in a rhythmic pattern. Every 200 milliseconds, the orientation shifted, then shifted back, then again at precise intervals. This isn't how a natural fast radio burst should behave. Magnetar eruptions produce chaotic magnetic fields. Supernova remnants scatter polarization randomly. Even the most exotic astrophysical objects show noise in their structure. But this signal showed order. Dr. Emily Chen at the SETI Institute ran the numbers through every known natural mechanism: plasma lensing, quantum vacuum effects, relativistic beaming. None matched. The pattern was too clean, too regular. Is this physics we don't understand, some undiscovered property of intergalactic space, or something else? Comment below before we reveal what NASA's AI found next. If you love uncovering these deep mysteries with us, make sure to subscribe and hit the like button. Because what followed wasn't just a signal, it shook Earth's own magnetic shield. At 3:51 a.m., for minutes after the signal arrived, something else happened. NOAA's Space Weather Prediction Center detected a sudden spike in Earth's magnetosphere. The magnetic field that shields our planet from solar radiation flickered for just 8 seconds, but the disturbance was measurable across every monitoring station from Alaska to Antarctica. Ground magnetometers recorded the anomaly. Satellites in geosynchronous orbit logged the compression. The magnetosphere's dayside boundary pushed inward by nearly 2,000 kilometers, then snapped back. NASA's first assumption was obvious: solar flare. The sun routinely bombards Earth with charged particles. When a coronal mass ejection hits our magnetic shield, it causes exactly this kind of disturbance, except the Solar Dynamics Observatory showed nothing. No flares, no plasma eruptions. The sun was in a quiet phase. Solar wind measurements were completely normal. For a moment, global monitoring stations thought a solar storm had hit. Technicians scrambled to find the source. They checked every satellite feed, every ground station, every space weather instrument in orbit, nothing from the sun, nothing from near-Earth space. The only electromagnetic event detected in that 4-minute window was the radio burst from Andromeda. This is terrifying because it shouldn't be possible. Radio waves don't push magnetic fields, they pass through them like light through glass. A distant radio signal shouldn't interact with Earth's magnetosphere at all. Yet, the timing was undeniable. Signal arrival at 3:47. Magnetospheric disturbance at 3:51. For minutes, the exact time it would take for a secondary particle wave traveling at near light speed to cross the distance from the outer atmosphere to the magneto. NASA's Goddard Space Flight Center pulled archived data. They found the same signature 18 months ago, a tiny magnetospheric blip recorded at 4:13 a.m. on January 17, 2024, 8 minutes after the first Andromeda signal. No one had connected them before. It seemed too subtle, too impossible. This is why NASA rushed into briefing mode. A second wave from Andromeda appeared to interact with Earth itself, not through gravitational force, not through radiation pressure, but through some mechanism that defies standard astrophysics. Radio astronomers did the math. If the source truly originated in Andromeda's core, the numbers were staggering. The signal measured at 140 Janskis at Earth's surface. For reference, the brightest fast radio burst ever recorded was FRB 202200610A. It peaked at 3 Janskis from a galaxy over 1 billion light-years away. This signal was 50 times brighter, from 50 times closer. Apply the inverse square law and the implications become clear. Brightness falls with the square of distance. Move twice as close, and something appears 4 times brighter. 50 times closer means 2,500 times the apparent intensity. The source energy required is almost incomprehensible. Scientists calculated that the burst released more radio energy in 3 seconds than our entire sun emits across all wavelengths in a full hour. Imagine a flashlight so powerful that even from the moon it could outshine the sun for a blink of an eye. That's the scale we're talking about. Dr. Vikram Patel at MIT's Kavli Institute ran the calculations 3 times. He thought his software had glitched, it hadn't. The brightness was real. Only 2 known objects in the universe produce bursts this energetic, colliding neutron stars and hyperflaring magnetars. Both are rare, both violent, both happen exactly once at a specific location. This happened twice, same spot, 18 months apart. The energy output doesn't fit any existing model. Magnetars don't store enough magnetic energy for a second eruption of this magnitude. Neutron star collisions can't repeat, they destroy themselves in the merger. Whatever created this signal has an energy budget that makes astrophysicists uncomfortable. But brightness wasn't the only problem. The signal carried something far stranger, information hidden in its timing. NASA's AI went deeper. The same neural network that flagged the polarization shifts began analyzing the signal's temporal structure, how the pulses were spaced, when they arrived, the gaps between them. It found something that made the entire analysis team stop cold: structured intervals. The signal wasn't a continuous wave, it pulsed. Each pulse lasted exactly 43 milliseconds, then silence for 86 milliseconds, then another pulse, then 172 milliseconds of silence. Notice the pattern: each gap doubled the previous one, 43, 86, 172, a geometric progression, binary doubling. In computer science, this is called exponential spacing. It's how digital systems encode information, how error correction algorithms organize data packets. It's not random. It's structured. The AI flagged 12 distinct pulse clusters across the 3-second transmission. Each cluster followed the same doubling pattern, but the number of pulses per cluster varied: 3 pulses, then 5, then 2, then 7. Dr. Sarah Brennan at Breakthrough Listen compared it to known astrophysical sources. Pulsars rotate and pulse, yes, but their timing drifts. Millisecond pulsars are incredibly precise, but they don't show geometric progression. They tick like clocks, not computers. Magnetar bursts are chaotic. Supernova echoes scatter randomly. Even the most exotic plasma physics creates noise, not order. Physicists say natural processes can create patterns, orbital resonances, quantum interference, standing waves, magnetized plasma, all generate rhythmic signals. But this one looked unusually clean. Too clean for most natural explanations. Some researchers pointed to an obscure phenomenon called plasma wake-field acceleration. When charged particles surf electromagnetic waves through ionized gas, they can create harmonic spacing. It's real physics documented in laboratory experiments. The problem? Achieving this across intergalactic space requires conditions we've never observed. You'd need a perfectly tuned particle accelerator the size of a galaxy. Possible in theory, never seen in practice. The analysis team ran every simulation, every natural model they could conceive. Most came close. None matched perfectly. The precision was the problem. Nature is messy, this wasn't. Then came the chilling realization, this second wave wasn't random, it may be part of a larger series. Scientists began asking uncomfortable questions. If 2 waves arrived 18 months apart, what about wave 3? Wave 4? Is there a schedule? One team at Princeton examined Andromeda's core more carefully. NASA's FEMI telescope has detected a mysterious gamma-ray excess there for over a decade, a concentrated glow of high-energy photons that shouldn't exist in such abundance. The leading theory blames dark matter particles annihilating at the galactic center. But there's another possibility. What if Andromeda's central black hole produces episodic bursts, a galactic heartbeat?